This video is Chapter 1, Part 2, where we will discuss atomic structure, electron configuration, valence electrons, and ions versus isotopes. So let's start with atomic structure. This is one of the very first things that you learn about when you start taking a general chemistry course. So this should be largely review. So first reminder, atoms are made up of 3 subatomic particles. Go ahead and just think to yourself, I think you know them. What are they? Protons, neutrons, and the one that you're going to hear most often in this course, electrons. So let's look at a diagram of an atom. The nucleus is made up of protons and neutrons. Electrons exist in the electron cloud. The mass of an atom comes primarily from the nucleus, so protons and neutrons are actually quite heavy. Electrons are a very, very tiny fraction of the weight of an atom. And the volume of an atom comes from the electrons. So if an atom is 1 to 5 angstroms across, the size of a nucleus is approximately 0.0001 angstroms. So obviously this picture is not drawn to scale, but the nucleus is very tiny compared to the electron cloud, which is kind of weird when you think about the fact that the nucleus is where all the mass of the molecule is. So let's talk about some definitions that we need to keep straight before we really move on to molecular structures and bonding. So first of all, when we say element, elements are made up of atoms of that element. So if you talk about carbon, you're talking about a carbon atom. This also includes diatomic elements. So diatomic elements are the elements that are found in nature as molecules of 2 atoms of that element. So there are several diatomic elements that you probably had to memorize at some point. You have nitrogen, hydrogen, oxygen, and all of your halogens, fluorine, chlorine, bromine, iodine. So those are the ones that you've probably been asked to memorize before. So hydrogen is found as hydrogen gas in nature. Oxygen is found as oxygen gas. Fluorine and chlorine are also gases. Bromine is a liquid and iodine is a solid. So the atomic number is equal to the number of protons in the nucleus and also the number of electrons in a neutral atom of that element. So in a neutral atom, meaning no charge, you should have an equal number of protons and electrons, and that number is the atomic number. There's also the mass number. The mass number is equal to the number of protons and neutrons in the nucleus. And this is because, again, electrons weigh essentially nothing compared to a proton or a neutron. And protons and neutrons have approximately similar masses. Compounds are made up of at least 2 elements bonded together. So examples would be C6H12O6. This is your general formula for any single unit sugars, and H2O is water. These all count as compounds because they have at least 2 different elements bonded together. So our nitrogen molecule up here is considered a molecule because it has 2 atoms, but not a compound because it doesn't have 2 different elements. A brief reminder about atomic orbitals. The main ones that you see are the s orbitals, the p orbitals, and the d orbitals. The s orbitals are spherical, the p orbitals have this peanut or dumbbell shape, and then d orbitals have this shape that some people call daisy, some people call double dumbbell, except for this guy, which looks like a pacifier. And then you also have the f orbitals, and they're not drawn here because there are quite a few of them, and their shapes are very unique. So I once had a student tell me that the way that they remembered it, I told them in class S for spherical, P for peanut, D for double dumbbell, and he said that he added F for effed up because he did not say effed, he said the full word, and I didn't know how to respond to that, but anyway, that's my story on atomic orbitals here. So those are your general shapes. Now, you've already learned about atomic orbitals, which is why I did not spend too much time on them. I want to refresh you on atomic orbital diagrams, and we're going to get to electron configuration from here. So you've probably seen this before. On our y-axis here, we have increasing energy. So our higher energy orbitals are towards the top, our lower energy orbitals are towards the bottom. Hopefully you recall that s orbitals are low energy, p orbitals are slightly higher energy, and d orbitals are higher than p orbitals. So as we are filling up our atomic orbital diagrams, there are a couple principles that you need to remember. First is the off-bow principle, which is that lowest energy orbitals are filled first. So let's think about an atom, let's say carbon. We're going to hear a lot about carbon. Carbon has the atomic number of 6. So it has 6 protons and it has 6 electrons. It also has 6 neutrons, and its mass number is 12. So if we were to put the atomic orbital diagram for carbon together, we would have to get 6 electrons onto this diagram. And you may recall that each orbital can only hold 2 electrons. And when we start filling our orbitals, we have to start at the bottom because electrons like to be lower energy. Before we start filling our orbital, we need to go through the rest of the principles. So the next one is the Pauli exclusion principle. Only 2 spin-paired electrons with opposite spins are allowed in each orbital. And so you might recall that you tend to draw the orbital or the electrons in as opposite arrows. So one up, one down. And this is our first 2 electrons of our carbon atom. And so we've fulfilled the off-bow principle and the Pauli exclusion principle so far. We started at the lowest energy orbital, and we put 2 spin-paired electrons in the orbital. What this means is that we did not put 2 up arrows here. We put 1 up, 1 down. So we can put 2 more in the 2s orbital, because that's the next one. And then we get to the 2p orbital, and there are actually 3 p orbitals in the second shell. And so this is going to lead us to our next principle, because we have 2 more electrons to place. Remember that carbon has 6. And this is Hund's rule. Hund's rule says we fill across degenerate orbitals with 1 electron each, then go back and add additional electrons. Degenerate means that they are equal in energy, that they are essentially the same, so no orbital will fill up first. Degenerate does not mean badly behaved orbitals, it just means that they are equivalent. So when you take your next 2 electrons, you're not going to put them in the same p orbital. You're going to spread them out over the p orbitals, and let's say that we had a higher atomic number element. We would have to continue to fill up our orbitals across using Hund's rule before we could go back and add in more electrons into those orbitals. But let's erase that and stick with carbon for now. So this is carbon's atomic orbital diagram. You also could have put the second electron here. It wouldn't matter. You could put one here, as long as you only filled 2 of them and they were in different orbitals. Another reminder, the electrons that are furthest from the nucleus are higher energy. S orbitals are kept close to the nucleus, and so they are lower energy. I keep saying higher energy and lower energy. What you hopefully recall is that the nucleus is going to have a positive charge because it is filled with protons. Electrons have a negative charge, and so think of magnets. It's actually quite easy for 2 magnets that are close together to slam towards each other and snap together. But if you try to pull them apart, that actually takes quite a bit of effort. And so that's how electrons and protons are. They want to be close together because they are opposites. Opposites attract. And if you want to pull them away from each other, it's going to take energy until you've completely removed them from each other. So think about your magnets again. You're holding two magnets together. You start to pull them away from each other, and that's actually quite difficult depending on the strength of the magnet. But then once you get outside the magnetic field, they are separate and they are no longer attracted to each other. The higher energy orbitals are actually living in that area where you're trying to hold the magnets apart. Next, we're going to talk about electron configurations. Electron configurations are a way that we can describe the locations and energies of electrons in an atom. This is essentially an address for each electron in an atom. So let's do some examples. In order to do these, we're going to need our periodic table. So I apologize if this is kind of small. This was the best I could do and give us space to write out the answers here. So before we actually do this, let's do some reminders about the periodic table. So when we're looking at a periodic table, we have some sections. So this first section is called the S block. Here is the D block. And then we have the P block. We also have the F block. And so these are atoms that have these orbitals essentially, but it's a little more complex than that. So as we're looking at the periodic table, we can also see the shells. So we have the first shell, second shell, third shell, fourth shell, fifth shell, sixth, and seventh. The F block has something kind of unique going on, and so does the D block. So you might recall at one point in Gen Chem, you had to kind of mathematically discuss at which level of an atom, which shell, certain orbitals were mathematically possible. And this is where it gets a little fun. So the D block, even though it starts in our fourth row here, D orbitals actually become possible in the third shell. So these are all 3D, 4D, 5D, and 6D. The F orbitals become possible in the fourth shell. And so even though they are out here floating literally nowhere, this is 4 and 5. So when I say, the S block, D block, P block, I'm not saying that boron only has P electrons and it only has the second shell. That's not reasonable. It's not what we're saying. What we're saying is that you can use the periodic table to kind of count the locations of electrons. So let's look at our example for carbon. We already did the atomic orbital diagram for carbon. We know that it has 6 electrons. We can use the periodic table to determine where all of the electrons live, and we can put out an electron configuration for carbon that tells us where all of its electrons live. So since carbon has 6 total electrons, one of its electrons is going to live in the 1s orbital, and so is another. And I know helium is off here in the p block. It actually belongs here when we're talking about electron configurations, even though it is in fact a noble gas. So carbon has 2 electrons that live in the 1s orbital. So that gives us one piece of this configuration. We're going to say 1s2. So 1 is the electron shell, s is the orbital, 2 is the number of electrons that live there. Now we have to go down to the next row. We have the 2s orbital, and since lithium and beryllium are both before carbon, we know that we're going to have a full 2s shell. So we have 2s2. So there are 2 electrons living in the 2s orbitals. And then we get to the second row of and we're in the p block. So we have 2 more electrons to identify, and they both live in the p block. So we're going to say 2p2, and that is the electron configuration for carbon, 1s2, 2s2, 2p2. One way to kind of check yourself is to, go through the periodic table for sure, But then also when you're done, add up all these little exponents that you've put here. It should equal the total number of electrons that you have in your atom. So 2 plus 2 plus 2 equals 6. For sodium, we're going to go a little farther. So let me get a different color for sodium. Sodium is in the third row in the first position of the S block. So if we're just counting electrons, remember we can use the other elements as kind of placeholders. Sodium is going to have 11 total electrons, and our placeholders are all of the 11 elements before, or 10 elements before sodium. So we're going to copy the first part of the carbon electron configuration. 1s2, 2s2, and then sodium is going to have electrons, 6 of them, filling the 2p orbitals. So 2p6. And then we have 3s, but there's only 1 electron that lives there. So 3s1. Now remember, if we add up 2 plus 2 plus 6 plus 1, that should equal 11, which is our atomic number for sodium. And go ahead and erase our other colors so far so we can keep going. Let's pick a new color for zinc. Now this is where it gets fun. Your transition metals are going to be located in the D block. So we have to get a little creative. Now there are a couple ways that you could do electron configurations. Sometimes people actually organize them by electron shell, but that's not technically correct because you want to list your electron configurations out in order of energy. And the way that the shells and orbitals are laid out on the periodic table actually does that for you. So you want to keep reading through the periodic table. So like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, all the way to the end here. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in the d orbitals because there are 5 types of d orbitals. So let's write that out. 1s2, 2s2, 2p6, 3s2, and then remember we're still hopping over here to the p block. 3p6, 4s2, 3d10. So if we add all these up, it should equal 30, which is the atomic number of zinc. So 2 plus 2 plus 6, that gives us 10, 12, 18, 20, 30. So that adds up. Now let's go a little further and get to bromine. And clean up the periodic table a bit here. So bromine, let's give it a new color, is over here. Oh, can't see that. That's just yellow. Bromine is over here. So let's go ahead and just say the electron configuration for bromine. And remember, we're just going to read across the periodic table. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then go back to 4, 4p5. So we would copy everything from zinc. And then tack on the 3p5, or 4p5, sorry. And that's the electron configuration for bromine. Now there is a shorthand way of writing out some of these longer electron configurations, and it's called the noble gas configuration. And in order to do the noble gas configuration, what you do is backtrack to the noble gas that was before your element. And you write that out in brackets, and then add on everything that comes after that. So argon is at the 3p6 mark. So what we have to add on is 4s2, 3d10, 4p5. Now this is a perfectly fine way to put an electron configuration, but when you're doing your homework, when you're doing quizzes, exams, make sure that you are reading the directions. If it asks for the full electron configuration, you're not going to get credit for this because I'm also looking for you to read off the periodic table correctly. So just make sure that you follow directions and that you don't do the noble gas configuration when it's not allowed. Whoops, okay, now our answers are going to show up. So let's talk about valence electrons. The whole reason that we're doing these electron configurations really is to get to the idea of valence electrons. Because valence electrons are the electrons that are responsible for chemical bonding, and they are the ones that are in the outermost shell of an atom. So this is going to be your highest numbered shell. So for example, if we look at the electron configuration of carbon, the highest shell is the second shell. So the valence electrons are all of the electrons that are in that shell. So 2s2, 2p2, carbon has 4 total valence electrons. And the shorthand for electron is E-. So you're going to see me use that a lot. Looking at sodium, its highest numbered shell is 3. So the valence electrons are the electrons in the third shell. Sodium has 1 valence electron. Now it gets a little more complicated when you start having elements from the D block, because the 3d10 electrons are at the end of the configuration, but they are not in the outermost shell. Our highest numbered shell is the 4th shell. So zinc actually only has 2 valence electrons. And same with bromine. Even though 3d10 is in between 4s2 and 4p5, it is only the electrons in that 4th shell that are valence electrons for bromine. So bromine is going to have 7 valence electrons. A fun fact is that the number of valence electrons is equal to the group number of the atom. So if you take a look at the periodic table, all of the elements that are in the first group, so the same column as sodium, are going to have 1 valence electron. All of the atoms that are in the same column as carbon have 4 valence electrons. All of our halogens have 7 valence electrons. All the noble gases have 8. The only place that this doesn't work is in the D block. So last topic in this video, I know this was a long one, is ions versus isotopes. This is a pretty simple topic. Ions and isotopes often get confused, but they are not the same. Ions are charged species. They are different from their parent element or compound by a number of electrons. So they've either been oxidized or reduced. Compounds can also be ionized if they vary by a proton or other chemical bond that creates a charge. Isotopes are not charged. These are atoms that have a different number of neutrons in their nucleus compared to their parent element, and therefore they are different from their parent element by mass. The atomic number does not change. So, for example, nitrogen-14 and nitrogen-15 have a different number of neutrons. Nitrogen-15 has 1 more neutron, therefore it is a little heavier than nitrogen-14. These two are isotopes of each other. Sodium and sodium plus are different from each other by 1 electron. So sodium has 1 valence electron. We just learned that in the previous section. Sodium plus has lost that 1 valence electron and has become ionized. So these are ions, or well, sodium plus is an ion of sodium. Sodium itself is not an ion. And then we have water and the hydronium ion. The name of hydronium ion actually kind of gives it away, but These are different from each other by 1 proton. So water is a neutral compound, but hydronium has 1 extra proton. So its structure is water plus 1 more proton. And it has a formal charge of +1 on the oxygen. So this is an ionic compound.